Welcome to the fourth practice exam part 2 screencast, and we'll pick up where we left off on the first screencast with question number 7. We have a chemical reaction, X plus Y makes W plus Z. Delta H is negative 150 kilojoules. So if each of these divisions is 50 kilojoules from our initial energy of X plus Y, the reactants, 50, 100, 150, the products, W plus Z, are 150 kilojoules lower in energy than the reactants. So from here down to there, that is our delta H value, and that's equal to negative 150 kilojoules. Now our activation energy is 75 kilojoules, so we from our reactants, X plus Y, we go up 50 and then 75. So our activation energy barrier looks maybe something like that. And this difference or distance here is our activation energy of 75 kilojoules. So that's this distance. Now, if we have an appropriate catalyst, what we know a catalyst does is it provides an alternative reaction pathway with a lower activation energy. So we'll use a dashed line, and we'll also use a different color. So in green here, what we can predict is that with a catalyst, we would expect a lower activation energy hill. And so what the appropriate catalyst does is the catalyst provides a different pathway, different reaction pathway. And that different reaction pathway has a lower activation energy E sub A. Because it has a lower activation energy, the reaction will be faster. The reaction is faster because we have more molecules that have an energy that's bigger than the activation energy. So they have collisions with high enough energy to make the reaction happen. So the reaction's faster because we have more molecules with with energy above the activation energy barrier, which means that they have enough energy to react. And then if we want to determine the activation energy for the reverse reaction, so W plus Z going to X plus Y, now we're going to start here, and we have to get over this activation energy barrier here. So that has to be overcome, so we have to go all the way up to there, and that's a distance of 150 kilojoules plus another 75 kilojoules. So the activation energy for the, let's call it reverse reaction, is equal to 225 kilojoules. So 225 kilojoules is the activation energy, which is 150 plus 75, the total energy needed to get over the activation energy barrier going that direction. Next up is question number 8. Here we have some values of the rate constant that were determined at different temperatures, and we are to find the activation energy for this reaction. Now, of course, what we know is that the activation energy is related to the rate constant. Their relationship is K equals A times E to the minus E sub A over RT. And of course, we can also put this in the linear form by taking the log of both sides. Ln of K equals negative E sub A over R times 1 over T plus ln of the constant A. And if we have as our x values 1 over T and as our y values ln of K, then this is a straight line with a slope of negative E sub A over R and a y-intercept of ln of A. So of course what this means is if we graph ln of K, our y value, versus 1 over T, our x value, we get a straight line, and we would have a slope that is equal to negative E sub A over R. So we'll do that. We will graph ln of K versus 1 over T. So these K values, we're going to have to take the log of them. And we'll do that to each one. Our T values, we have to do our temperatures in Kelvin, so we're going to add 273 to each of these temperatures to have it in Kelvin, and then we're going to do 1 over our values for each of these 4 data points. And if we do that graph, we get a pretty darn straight line. And what we get for a slope when we make this graph is we get a slope of about negative 12,650 Kelvin, and that's equal to negative E sub A over R. So solving for E sub A equals the negative of the slope, negative 12,650 K, times R, and let's do our R in kilojoules, 8.3145 times 10 to the minus third kilojoules per mole Kelvin. And Kelvin will cancel, so we'll end up with a value in kilojoules per mole. And negative 12,650 times 8.3145 times 10 to the minus third equals, rounded off to 3 sig figs, 105 kilojoules per mole. And that's our activation energy value. Okay, so the next question, number 9, we have a reaction. We have a rate law for that reaction, and we have a proposed mechanism. And first up, we're asked to state if we have any intermediates. Well, an intermediate is made in one step, like Cl is made in step 1, and used up in a subsequent step, like step 2, it's used up. So Cl would be an intermediate. Now COCl is made in step 2 and then used up in step 3. So COCl is an intermediate as well. For something to be a catalyst, speeds up the reaction, but it's not used up in the process. So a catalyst, we'd have to start with the catalyst and then end up with the catalyst and essentially regenerate it from one step to the next. And we don't have any situations where that occurs. Now next, we're to find the rate law for this mechanism. And first of all, it's always worth double checking that the steps of the mechanism do in fact add up to the overall. And so just a quick check on that. If we add up step 1 plus step 2 plus step 3, the 2 CLs on the right on step 1 cancel the CL on the left on step 2 and the CL on the left on step 3, and so those cancel out, and then the COCl made in step 2 cancels out with the COCl used in step 3, and so we end up with CO plus a Cl2 makes COCl2, which is the overall reaction. So our check works. This mechanism at least fulfills the condition of the the steps do add up to the overall. Now, to determine the rate law from the mechanism, of course, we always start with the slow step, which is the rate determining step. And since these are elementary steps, we can state the rate law for an elementary step simply from the stoichiometry. So the rate for the overall reaction is the rate for step 2, and the rate for step 2 is some rate constant for step 2 times the concentration of CO. So there's the reactant in one of the reactants in step 2, and then times Cl, which is the other reactant in step 2. So CO times Cl. Now the problem is Cl is an intermediate, and we can't have an intermediate in our rate law. So we're going to have to get rid of our intermediate, and how we can get rid of the intermediate is we take advantage of the fact that step 1 is fast equilibrium. And so since we have an equilibrium step, then the rate for step 1 going forward and the rate for step 1 going in the reverse direction, going backward, those two rates are equal. And again, since these are elementary steps, we can get the rate for step 1 going forward. Well, it's just equal to the rate constant for step 1 going forward times the concentration of Cl2. And going the other direction, the rate for step 1 going in reverse is the rate constant for the reverse reaction times Cl. And this one is to the second power because the stoichiometric coefficient is 2, and that becomes the exponent because it's a step, an elementary step only. So just remember, these are elementary steps. That's the only reason we can do this. Okay, well, from this, can we solve for Cl? Sure, we can divide this side by K reverse and divide this side by K reverse, and so those cancel out. And then that leaves us with Cl squared. And how we get rid of a Cl squared is then we will square root both sides. So we'll square root this and square root that. And so we have K forward over K backwards times Cl2. And that whole thing is square rooted. So that's actually the same as to the 1/2 power. And then that's equal to, remember that these k's canceled already, so square root of Cl squared is Cl, concentration. And that gets substituted for the intermediate, which we need to get rid of. So if we do that substitution, then we have rate equals K2 times K forward over K backward times Cl2 concentration, and all of that is to the 1/2 power. And then we also have the concentration of CO, which was our other substance. So the Cl substitution gives us all of this stuff, and then we have CO. And notice that all of this stuff is just simply a constant, so we'll just call that K. And let's rewrite this just slightly now. Rate equals some constant K, which is all of these other constants lumped together. And then we'll just keep it in the order that we had before, so let's reverse these again. Concentration of CO times concentration of Cl2 to the 1/2 power. So that's the rate law we get from this mechanism. And worth noting, the actual rate law and the rate law we get from the mechanism that was proposed compare, and they are in fact the same. One, how did we get the correct rate law? We always get rate laws from the appropriate experimental data. This question didn't provide what the data was, but that's where the rate law came from. And then if the known correct rate law is matched by the rate law for the proposed mechanism, which is what we had in this case, what that means is the mechanism is plausible, or if you prefer, we could say possible. It might be right. We don't know for certain it's right, but we know it at least has the potential to be right. It might possibly be correct. Next up is a question dealing with some nuclear chemistry. And first one, nuclear equation for the alpha decay of fermium-244. So fermium-244, if we check a periodic table, fermium-244 has an atomic number of 100. And if it undergoes alpha decay, it gives off an alpha particle, which is a helium nucleus. And then if the mass number goes down by 4, that leaves us with 240. If the atomic number goes down by 2, decreases by 2, that leaves us with 98. And that is the element californium. Now to estimate the half-life of fermium-244, if we start with 1 nanogram, then the time it takes to get to half of that, or 0.5 nanograms, is about there on the graph. And if we do kind of our best estimate here, it looks like that's, well, more than 3 and less than 4. So we're kind of making an estimate here, definitely, but maybe 3.3 or so milliseconds. And different people might estimate 3.4 or 3.2 or 3.5 or something, but somewhere in the ballpark of 3 something milliseconds. Okay, so the next question, we have phosphorus 32, which is a beta emitter. And first of all, we need the balanced nuclear decay equation for the beta decay of phosphorus 32. So phosphorus 32, phosphorus has an atomic number of 15. It undergoes beta decay, so it emits an electron, and the remaining particle must have a mass of 32 and an atomic number of 16, because 16 plus -1 equals 15, and that is the element sulfur. Next, how many beta particles are emitted in one day if we have a 5 milligram sample of phosphorus 32? Well, what we know is that the rate of decay, or the activity, is equal to the decay constant, or rate constant K, times the amount of, in this case, phosphorus 32. And we also know that the decay constant, or rate constant, is related to the half-life, which we know by K equals ln of 2 over the half-life. And that's ln of 2 over 14.29 days in this case. So that works out to be 0.04851 per day. Now, to get the number of beta particles emitted in a day from this 5 milligram sample, well, if we calculate the rate of decay per day, then that's approximately the number of beta particles emitted in a day, if we assume that the rate of decay is fairly constant over the course of a day. Now, of course, the rate of decay is always changing. As we have less and less substance, then we have less and less rate of decay. But if the half-life is 14.29 days, then in one day, not that much of this is actually decayed, and so the rate would not be that different at the end of the day as it was at the start. So that's a pretty good assumption for getting a fairly decent estimate of the value. So we'll calculate the rate. It's K, which is 0.04851 per day, times the amount, which is 5 milligrams. So let's make that grams. 5 times 10 to the minus third grams of phosphorus. So this would give us how many grams of phosphorus decay per day. And we need to convert the grams into, first of all, moles. The isotope phosphorus 32 is about 32 grams per mole. So grams of phosphorus will cancel. And then we want how many particles are emitted. So what we know is, and let's just go to the next line to have some space here. There are 6.02 times 10 to the 23rd phosphorus atoms per mole of phosphorus. And that gives us a cancellation between moles of phosphorus, or of moles of phosphorus. And then that gives us atoms of phosphorus. And then for every one phosphorus atom, it can undergo one decay. And so that allows us to convert from atoms of phosphorus into beta decays. And if we then take 0.0451 per day, multiply by 5 times 10 to the minus third, divide by 32, multiply by 6.02 times 10 to the 23rd, we end up with 4.6 times 10 to the 18th decays in one day, or per day. And that is a pretty good approximation to number of decays in a day. Okay, and the last part, if we start with 5 milligrams of phosphorus 32, how much remains after 6 weeks? Well, nuclear decay follows first order kinetics, so the amount at some time is equal to the initial amount times e to the minus kt. And of course, our initial amount is 5 milligrams. Our k is 0.04851 per day, and then that gets multiplied by a time of 6 weeks. But weeks and days, units don't jibe, so we will note that we have 7 days per 1 week, and so weeks are converted into days, and then the units of days will cancel. And if we then take 5 milligrams times e to the minus this whole exponent all multiplied together, we get 0.652 milligrams for our answer. Next up are a couple of nuclear equations to balance. First of all, barium, which has atomic number 56, undergoes positron emission, so it emits a positively charged electron, and that leaves the daughter nucleus after positron emission having a mass number of 125, an atomic number of 55, and that is an isotope of cesium. Uranium-235 undergoes fission, uranium's atomic number 92, neutron has no charge, barium number 56, neutron, no charge. So 235 plus 1 is 236. On the right, 140 plus 3 is 143. The difference, or the missing mass, so to speak, is 93. Dealing with atomic number, 92 plus 0 is 92. 56 plus 0 is 56. So 92 minus 56 is 36 for the atomic number difference, and that is an isotope of krypton. Question 13 deals with radioisotopic dating, and this is going to be for living organisms or formerly living organisms which contain carbon-14. Radioisotope with a half-life undergoes beta decay with a half-life of 5,730 years, and living organisms maintain a constant concentration of carbon-14 because they're constantly taking in and getting rid of carbon. But when an organism dies, then the carbon-14 that was in it when it died doesn't just stays there, but it undergoes decay, and so over time there's less and less carbon-14. And by comparing the decay rate of carbon-14 in a formerly living organism like this mummy with the decay rate in a living organism, we can estimate its age. So note this all hinges upon the fact that the activity, or the decay rate, is directly proportional to the amount of the radioactive substance, which in this case is carbon-14. And this is true in general, and of course this is first order kinetics. So since it's first order, the time is equal to -1 over the decay constant K times ln of the amount at time t compared to the amount at time 0. And since the amount of carbon is proportional to the activity, then we can have the ratio of activities, and then the natural log of that is equal to the ratio of the amounts. And then, of course, our relationship for K is the ln of 2 over the half-life, which in this case is 5,730 years, and so that works out to be 1.21 times 10 to the -4th per year. So the time that has passed from when the mummy, when the person who became the mummy died, to now, that corresponds to the amount of material that we started with compared to the amount of material we end up with, that material being carbon-14, and that's the same as the ratio of the activities. So we have -1 over 1.21 times 10 to the -4th per year. Oops, forgot the per year there. And then times ln of the activity at time t, that's now 5.9 decays per minute per gram of carbon. And then that's compared to the when it was living, 13.6 decays per minute per gram of carbon. And so the result we get from this calculation, 6,900 years. Okay, the next question, we have two different isotopes that we are to predict the likely kind of radioactive decay they undergo. First of all, bromine 85. Well, stable bromine, if we look on the periodic table, it appears that stable bromine would probably be roughly bromine 80, because the listed atomic mass, which is the average of all the naturally occurring isotopes, for bromine it's pretty close to 80, so probably the stable isotopes have a mass of, or the most stable isotope has a mass of around 80. Well, comparing 85 to 80, 85 is bigger, so the mass is due to more neutrons. So we would say that bromine 85 probably has too many neutrons compared to the stable isotope. And what a neutron can do is it can undergo radioactive decay to make an electron and a proton, and that makes one less neutron and one more proton. This, of course, is beta decay, and that would get the unstable bromine 85 isotope closer to stability, and it'll no longer be bromine, of course, as well. So we'd predict beta decay. Now for strontium 85, strontium, using the same method, probably has a stable isotope with a mass number of around 88. That's about the average atomic mass of strontium, so probably the most stable isotope has about that mass, and 85 is less than 88. So this has we could either look at this as too few neutrons, or we could also look at this as too many protons. And too many protons or too few neutrons both end up having the same thing that can happen to redress that imbalance. One is electron capture, and the other is positron emission. 15. Which of the following isotopes has the largest binding energy per nucleon, and the highest binding energy per nucleon is iron 56. So manganese 55 is pretty darn close to that. That's the peak of that binding energy versus number of nucleons curve that looks like this. The peak is at iron 56. So manganese 55 is closest to iron 56. So we'd expect that to have the highest binding energy per nucleon. 16, we have a nuclear reaction. It's a big nucleus, uranium-235, breaking apart into two smaller nuclei, barium-141 and krypton-92, with a delta H of negative 2 times 10 to the 10th kilojoules. And that is, of course, an exothermic reaction, lots of energy given off. And big nuclei breaking apart into smaller nuclei is nuclear fission. Whether it's nuclear fission or nuclear fusion, or for that matter building a nucleus, the mass of the product is going to be less than the mass of the reactants. The quote-unquote lost mass turns into energy of the process. And the relationship is that the change in energy, or the amount of energy given off, is equal to the change in mass times the speed of light squared. And so if we're trying to find the change in mass, that's equal to the change in energy divided by c squared. Our change in energy is negative 2 times 10 to the 10th kilojoules per 1 mole of uranium. So this number of kilojoules is if 1 mole of uranium-235 undergoes reaction. So if we have 1 mole of uranium-235, then this is the amount of energy that's given off. To do our calculation, we're probably going to want to convert kilojoules to joules. So 1 kilojoule is 1,000 joules. And the reason for doing this is because 1 joule is the same as 1 kilogram meter squared per second squared. And we're doing that because what we do with the delta E is we divide it by c squared, which is 2.998 times 10 to the 8th meters per second squared. And when we do the calculation, the value you get, or we get, is negative 2.2 times 10 to the minus 4th. And then the units are going to be meters squared over seconds squared, cancels with meters over seconds squared here. And so that leaves us with units of kilograms. And that is the amount of mass change. It's a mass quote-unquote lost. And the very last question, we have a radioisotope, which has a half-life of over 1 billion years. And how much time has elapsed for this process that's shown here? Well, of course, we have to remember that radioactive decay is first order. And first order processes have a constant half-life. And since the half-life is constant, then we can say, well, we start with 16 of these nuclei. We end up with 2. And so the amount of 16 going down to 8, that's 1 half-life. And then of 8 decreasing to 4, that's a second half-life. And then of 4 decreasing to 2, that's a third half-life. So we have 3 half-lives total that occur. 3 half-lives of 1.28 times 10 to the 9th years totals up to 3.84 times 10 to the 9th years of time elapsing. And that's it for the practice 4th exam key.